Hello and welcome to this video from Heybridge High School Maths Department, and this video is about velocity time graphs. So as you can see from the graph on the screen, velocity time graphs have a number of important features. So when the gradient slopes upwards from left to right, that shows acceleration. When the gradient slopes downwards from left to right, that shows constant deceleration. And the steeper the slope is, the quicker the acceleration or deceleration. And a horizontal line shows that you're travelling at a constant speed, so your velocity is remaining the same. It's important to remember that velocity is a vector quantity, so it has both a magnitude, which is the speed, it's the size of the velocity, so how fast you're going, and then you also have a direction. So velocity, you've got to be travelling in a certain direction. And this area underneath the graph represents the displacement. And the displacement is how far you've travelled from your starting point. So let's have a look at our first question. So Dowie was a cyclist. He travelled along a straight flat road to the bottom of a hill and cycled up the hill. The gradient of the hill was constant at first, then decreased near the top, where Dowie stopped for a rest. Dowie maintained the same level of effort throughout his journey. Which of the following velocity time graphs represents Dowie's journey? Well, we know that Dowie is maintaining the same level of effort throughout his journey. So on the initial flat section of road, he must be travelling at a constant velocity, a constant speed. And if he's travelling at a constant speed, then we need to have a horizontal line on our graph. So that's immediately going to rule out graph C and graph A. Now it says that he gets to a hill. So when he gets to a hill, he's going to slow down. He's going to decelerate. Graph A shows that he accelerates. So let's get rid of that one. Okay, so he's going to decelerate, and then there's going to be another flat section because he's going to maintain a constant speed. He's actually going to decelerate quite quickly as he's going up this hill. And then near the top, the gradient's going to decrease. So if he's still putting in the same amount of effort, he'll have a short amount of time where he actually accelerates because he's putting in the same amount of effort, but he's cycling up a smaller gradient. So that's going to rule out this one. Okay, so we're going to be left with graph D. So as we can see, this first section here is the flat section. Then as soon as he hits the bottom of the hill, he's got to go up this really steep gradient. So he's going to decrease quite quickly. And so he's going to, decelerate quite quickly. And then we'll have this flat section where he's going up the constant gradient at a constant velocity. And then as he gets near to the top, the gradient's going to decrease. So because he's still putting in the same amount of effort, he's going to accelerate slightly, and then when he gets to the top, he stops. So he immediately decelerates down to a velocity of 0, which means that he isn't going anywhere. So the answer to this question is D. So now we've got a second question, and Sian went for a ride on her bike. And she started her ride at 1400, and the graph below shows some information about her bike ride. So question A, during which quarter-hour period was Sian's acceleration the greatest? So what we're looking for here is during which quarter-hour period was is the gradient of the graph steepest? So if we kind of split this down here into quarter hours, we can see it's going to be somewhere along here. Oh, and I would actually suggest that it's here. Line's a little bit wonky. but there we go. So I would say that from 1430 to 1445, Sian's acceleration was the greatest, because that's the section of the graph that goes up most steeply from left to right. And at about what time did Sian stop accelerating? So we want the point at which the graph goes flat, which is around here. So we're going to say around about 1515. So now we've got this question. A train manufacturer has developed a new braking system. The velocity time graph shows the velocity of a train from when the brakes are applied until it comes to a rest. So this clearly shows deceleration, because from left to right the graph slopes downwards. It's not constant deceleration though, because it's not a straight line sloping downwards from left to right. So for question A, we're being asked to estimate the train's deceleration at time 60 seconds. So what we need to do is we need to find, if we had a straight line, then we just find the gradient, and that would show us the rate of change, and the rate of change would be the deceleration. Because we've got a curve, we want to know the deceleration at 60 seconds, which is here. So what I've done in red is I've drawn a tangent to the curve, and I'm going to find the gradient of that tangent. So the gradient is the change in y over the change in x. So if I have a look at my y-axis, I can work out my change in y. So I've got 5, 10, 15, 20.5. And because it's sloping down, that will actually be negative 20.5. And then I'm going from 43 to 80, 70. Yeah, 43 to 70. 70 take away 43 will give me 27. And that gives me negative 0.76 to two significant figures. That's negative because it's a deceleration, so it's the opposite of acceleration. So if we want to write this as deceleration, we just put it as 0.76 meters per second to the -2. Now we're going to look at question B. So we need to calculate an estimate of the distance travelled by the train from the instant the brakes are applied until it comes to rest. So I need to calculate the area underneath the graph. So as you can see from the red line, we split the area up into trapeziums and triangles. If you have a graph that has a flat line on, so a horizontal line, because there's a constant velocity, then you would use a rectangle or square for that. So if we have a look at A, so A is a trapezium. So we're going to do half of 36 plus 34, and then we multiply that by the width or the height, so that would be h for this trapezium, multiplied by 20. So I'm just going to work that out. So 36 plus 34 is 70, half of 70 is 35, 35 times 20 is 700. So you can now see all of the calculations there. So A, B and C are trapezia. So I have done half the length of the parallel sides, half the sum of the parallel sides. So I've added the two parallel sides together, halved that, and then multiplied it by the width or the height, h, which is 20. And that gives me the three answers for A, B and C. And then D is a right angled triangle. So I've just done half multiplied by the height, which is 19, multiplied by the base, which is 20, and that's given me 190. And all of these are in meters because they're distances. And then I just need to add all of these together, and that will give me an estimate of the total distance travelled by the train. So the train's travelled about 2,000 metres. Okay, and this is our final question. So we've got two runners, Katrin and Delith, and they start a race at the same time. And the velocity time graph shows their velocities over the first 5 seconds of the race. So question A, at the start of the race, what was the earliest time that Katrin's acceleration was 0 meters per second squared? So we need to look for the point at which the gradient of the graph is 0, which is going to be here. So that's going to be after 1.7 seconds. Okay, now we've again got to use these trapezia and triangles to calculate how far Katrin has travelled in the first 5 seconds of the race. So we're going to have A, B, C, D and E, because this time we've got 5 shapes, as we can see from the question. It's saying to use the velocities at t equals 0, t equals 1, t equals 2, t equals 3, t equals 4 and t equals 5. So that's why I've marked the vertical lines onto the graph as shown here. I've basically split the graph up into 1 second time intervals, and then I'm going to calculate the distance that she travelled over each second. So I've worked out the area of triangle A by doing half times base times height, and then I've worked out the area of the 4 trapezia B, C, D and E by doing the sum of the 2 parallel sides multiplied by the height and then halving that answer, and then I add together all of those areas, and that gives me 19.75 meters. Okay, and then we have question C. Calculate an estimate of how far Katrin was ahead of Delith after 5 seconds. So we can quite easily work out how far Delith's run, because Delith's accelerating at a constant speed. So we can just work out the area underneath the line that represents Delith. So Delith is 3 meters per second. So Delith has travelled half times the base, which is 5 seconds, so times 5, and the height of the triangle, which is 3. So Delith has actually only travelled 7.5 meters. So if we then work out the difference, we're going to have 19.75 minus 7.5, which will give us 12.25 meters. So after 5 seconds, Katrin was about 12.25 meters ahead of Delith. So question 2, explain why your answer to C is an underestimate. Well, if we actually have a look at the area that we worked out underneath the graph for Katrin, there are these bits at the top here that we haven't been able to include. So it's because we haven't worked out the exact area underneath the graph representing Catherine. We've only been able to work out an estimate, and there are parts of that graph that aren't included in the area, so therefore it's an underestimate.